So once again, I'm Stephen Hillion, co-founder of Alpine, and Chester is our director of platform engineering. So he's built the analytics engine, part of which we're going to describe today. What we do is we have built this platform that mostly medium to large corporations use if they want to have the power of a system like Spark to do complex machine learning, but don't necessarily know where to get started. We want to talk today about the challenges we've had in working in and around these large-scale parallel platforms like Hadoop and MPP databases, and how we've leveraged Scala in particular, and also Spark, as a mechanism for doing that while hiding some of the complexity from our end users. So we'll talk in some depth about a couple of instances of that, although we've actually done that in many different forms and functions. Here's a quick sort of very high-level architecture diagram. Essentially what we've built is a parallel analytics engine that interfaces with large-scale databases, with Hadoop MapReduce, with Spark, with cloud platforms as well. Allows you to do large-scale machine learning without having to write a lot of code, and essentially to be ignorant of what the underlying data platform is. Not willfully ignorant, but not have to worry about the complexities of that platform. Around that core parallel analytics engine, we've built a library of machine learning functions, often contributing those back to libraries like MLlib, often leveraging those, and then wrapping that within a visual workflow interface that users of, say, Pentaho, for example, or to SPSS Miner would be somewhat familiar. Now that's introduced a lot of complexity. We have this very easy-looking interface, as you'll see here, and that hides a lot of the complexity. So how do you take these complex algorithms and parallelize them across a broad variety of different data platforms? That's complicated enough, but how do you then tune those platforms? How do you monitor the progress of your job? How do you handle bad data? How do you deal with reporting error messages? And so on and so on. All of those things need to be encapsulated in this analytics engine and made as simple as possible for the end user. So some of the examples of the things where we've had to innovate and leverage Scala in order to make things more straightforward in a way that Chester's going to demonstrate is, for example, building a simple visual interface that masks that complexity. Providing access to a broad variety of different data platforms, but essentially viewing all data as sort of equal, whether it's a table sitting in a database or a Parquet file sitting on HDFS. Another level of complexity is we want to give access to multiple languages. Even though we've built this visual interface, we want to make sure that people can sort of break out of it and leverage something like R or Spark natively, or Hive, or Pig, or MapReduce, or whatever it might be. So we wanted to provide language support. We then wanted to go beyond that and actually make it extensible. So if you wanted to provide specific functions and have those available to all of the end users through a visual interface, you could do that as well, essentially a plug-in architecture for these visual operators. Of course, the kernel of this is actually taking some of these algorithms, whether that's something like a logistic regression or something as simple as a row filter or a histogram or a box plot. We want to make those run fully in parallel and have the user not have to worry about how to tune those algorithms to make them run fast. And then be able to do that interactively and be able to visualize and model just as simply as if you were doing this in Excel. And then also be able to monitor and manage the progress of those. It's actually one of the most challenging things that we have to do today. And that's one of the things that Chester will drill into in a second. So the idea I'm trying to get across is that while the outward interface is very simple to the user, it's masking a lot of complexity. And we've really, of all the languages and technologies we use, I think it's chiefly Scala, which forms the backbone of all of the programming that we do, and Spark as sort of the flagship platform for us for deploying these large-scale machine learning jobs. So Chester will go into some of the technical details about how we've done that.
So how do we leverage in Scala and Spark? So we have using Scala and especially R-Akka for many different things. So for example, we're using Spray and R-Akka for the REST APIs. We're using R-Akka to building our R-Akka R servers to get around the problems of this copyright licensing issues. So we also using R-Akka for agent architecture. You'll see in a second, and we're using, of course, using Scala with Spark. But in this talk, and because we only got 20 minutes altogether, so we want to focus in one particular part. So how do we integrating Alpine integrated with the Spark. So in particular, how do we build up the communication channels for Spark? So here's briefly, this is our agent architectures. So because Alpine have to support, all kind of Hadoop distributions from, MapR to Hortonworks to Cloudera and a different version of these distributions. And each distributions may have different protocols, protobuffs could be different, and API could change. So essentially, from the same user interface, how do you access different type of data source without, different deployments? So we're using R-Akka, to sending messages from Tomcat to the agent. Each agent essentially R-Akka systems allow you to talk to a particular type of Hadoop distributions or different version of Hadoop distributions. So, and also these agents also talk to relational database, and we support Greenplum, Teradata, GDBCs, and any others flavors of stuff we support. So with that in mind, and say, okay, now how do we integrate with Spark? And so in particular, we want to discuss two pieces. One is a different type of a Spark deployment mode, and the other one is how do we build this task communication channel. So why we mentioned about the deployment mode? So essentially, as everybody knows, Spark has a different type of deployment mode. It's a standalone mode. There's a deploy in the Yarn or using Mesos. Even in Yarn, there's two types: the Yarn client and Yarn, Yarn cluster. So if you look at these pictures, we're talking about Yarn client and Yarn cluster. Yarn client is basically the Spark drivers on the client side and the Spark jobs in the Yarn container. And while Yarn clusters, all the both driver and the Spark jobs in the container. So here comes the problems. So if you're using Yarn cluster, this essentially turns into a batch jobs. So we have to use a Yarn cluster because our application is used by many different clients, and they wrote all kinds of Spark jobs, and we have no control of. So if somebody decided to write a bad one, for example, aggregate a lot in the Spark driver, you crash the JVMs, essentially crash everybody else's jobs as well. So we need to use the Yarn cluster mode. But the Yarn cluster mode essentially, as I said, it's essentially become a batch job. There's no communications, no reporting. There's essentially just wait for, if you run 10 hours, you have to wait for 10 hours to get it back. So we want to change that. We want to see how do I monitoring where the job's going. If job run 5 hours, you see something wrong, you want to stop it, right? So essentially, we added three major changes to the Yarn client. So in order to do this, we essentially have to fork the Spark Yarn clients module. So first one, we add the Yarn application listener. Essentially allow us, adding a new listeners allow the Yarn container when start, stop, and can give us callback. The second part, is on the Spark Yarn client, we add a stop, kill application APIs, which is simply take an application ID and call kill application. The third one is we add a callback for resource. Resource callback allows to estimate how much resources the Yarn has. So this is the first part. Adding Yarn application listener essentially gives us something like this. First, he gave me a Yarn progress indicator. So he tells me you got 0%, 10%. And gave me an application ID, which I, in turn, can use for stop the jobs. And the third one gave a Yarn application tracking URIs. So if you look at the Spark source code on the Yarn client, essentially what we change is something like this. There's a method called a monitoring application, which is a while loop, just waiting for the Spark job to finish. In there, once the state changes, we essentially call the application listener to notify application progress, application failed, any of these state changes. So essentially, you got notified once the state had changed. And on the application side, our agent side, essentially, once we get these callback, we're using R-Akka send a message to our applications, and which can learn then to log it or do something else. So what this functionality enable us to do this first part. So you notice when the Yarn application starts, before the Spark job actually starts, we already have a tracking URL there which can bring you to the cluster page. And have a progress bar tells you to 0 or 10%. And also, because we have application ID now, we can use the stop button, essentially calls the API to kill the job if we want to stop it. So this is really gave early feedback for the users, even before the Spark job starts. So the next part is, okay, so go to the actual Spark, submitting the Spark jobs. As everybody knows, if you want to submit a Spark job, essentially you need to provide the driver's memories, number of executors, and how much memory you need for each executors in a course. So the problem is you have to essentially estimate what you need beforehand. If you're giving too much and the job got killed, because basically Spark essentially have this code saying that if the job is over the maximum of the container plus the overhead, minus overhead, essentially job got killed. So, and also you don't know what, the data could be very small or could be very large. So these are very hard to control how much memory you need. So what we did is essentially we modified the Yarn client's APIs to essentially passing a function. This function is we call a Yarn resource capacity, which contains the memories the containers has and the number of cores on the container has. This function is called from the Yarn before the job starts. So this way, this provides us this. First, we are allowed to reset the memories if the user asking too much of the memories. Because at this point, we already know how much max memory the container has, and we know what's the overhead. So if it's asking too much, we just reset it to the maximum so you can continue instead of job get killed. And the second one is, if you happen to have the file size, you already know your file size. Now you combine it with the max memories you already get it from the callback, you can do a better estimation dynamically, programmably, to give you better driver memories and executor memories. So, but there's a reason. With the recent Spark and especially the Spark after 1.3.1, and they added this Spark dynamic allocations. So this allow you to basically Spark allow you to dynamically increase or decreasing the number of executors, but you have to specify per executor how much memory in the cores you have. But at least this solves one of the problems. But we still have to estimate the driver memories. And so we don't like fork Spark, so we will gradually reduce our forked changes. But we'll still have to somehow find a way of estimating the driver memory as well as how about the Yarn listener part. So this is our first changes. The second part of changes about the task communication, as I mentioned, that it's a batch job in the Yarn cluster mode. There's no communication back. And how do you find the error reporting? How do you find the live progress reports? So what we did is this. When we're submitting the Spark jobs, essentially we create a Spark client listener on the agent side, on our client side. So this one has a Spark URI. We basically send, along with all the other configurations, we send to Spark this URI. On the Spark job side, from Spark context, the Spark context actually have this actor systems. We can create an actor out of it. So we create an actor called a relay messenger actor, which can do a handshake with our client-side Spark listener. And once this handshake is done, the communication is established. And then we can communicate after that. So inside the cluster, when the job starts, we create something called application context, which resolve the client-side Spark listener actor. We create a new actor, and then we create a logger using this. And then relay the message over. On top of that, we also create a Spark listener, and we will see in a second to get the progress. The loggers essentially sending different type of messages. And then our print statement also redirect to the logger. So this way, it's on the client side, you can see different logs. Actually, even you write a log on the print statement or on the Spark job. So this is what it looks like. So on the Spark context, this listener bus, you usually, by default, you have these job progress listeners and event log listeners, which goes to Spark UI and Spark history log, separately. We create a new one, this is job progress relay listener, which sending R-Akka messages to our agent. And our agent, in turn, send a message to our Tomcat, which using WebSocket to directly update our Spark UI, our Alpine UI. So this is on the Spark side. For example, on this is this listener detecting the stage already finished, the task, the Spark job stage finished. Once job's finished, we, using the logger, send a UI message to our agent. So as you can imagine that we actually have different type of messages from the actor, from the jobs logger sent to the agent side. There's a log type, there's a UI type, and there's application type. So the UI type could have a progress bar, could be a start message or end task message, or simply display something. So on our client agent side, we have this listener. Once he got the log message, we directly send to Log4j, and we're just logging on our client side. If it is a UI message, and we see it's a progress bar, we display a progress with the tracking URLs. If it is a counter, we display counter. So there's all kind of things you can display. And if it is application message, we essentially update the status of the job and all the other things. So with this way, we essentially develop a very general communication channel from in this young cluster deployment mode, and allow us to actually see without going to Spark and actually refreshing the pages, and actually see a lot of things going on. So the end result is something like this. So when we start a job, the Spark UI, essentially the equivalent Spark UI, directly displayed on our UI without refreshing pages. So if you go to Spark UI, you keep refreshing pages and see where the job has been progressed. Here, because of using WebSocket, all the things are live streaming directly to you. So our user can directly see this. So that's kind of just, we can, because we only have a very short time, so we focus on various subset of what are we doing. So we have a lot of other projects with Spark we're working on. There's a machine learning project we're working on, and there's also a long-running Spark job we're working on. We're working on a visualization framework called Chiasm to allow us to basically doing the visualization, talk to Spark, and that requires a long-running Spark jobs, and we're using R-Akka to run that. We're probably going to report that maybe next time or next year sometimes. So with that, I turn back to you.
Okay, I want to make sure we don't run over time, so and leave time for questions. But just maybe a final thought is that as we've been emphasizing, the purpose of this. Oh, that's right. Just to sort of summarize this and give an example of how we've been using it. One client in particular that I think was struggling to do, this is a financial services client, they were doing sort of credit reporting, credit scoring, essentially trying to build predictive models around very large quantities of transactional data and customer demographic data. And in order to do that, they were leveraging a traditional platform that took them about 72 hours to refresh their models every, I have no idea actually, maybe every month or every week, something like that. By leveraging Hadoop, they managed to reduce that time to about 50%. What we were able to do is go in and rebuild those same workflows, essentially rebuilding them leveraging Spark, but again, hiding all that complexity. So in particular, the specification of number of executors, for example, and the amount of memory that Chester was just talking about, or specifying what particular operations would run, was all essentially taking care of the engine. So really the purpose of everything we've been talking about is to try and encapsulate in a single engine all of this complexity that you need for doing configuration of jobs and submission of jobs and error reporting, as well as, of course, the parallelization of the algorithms themselves. So certainly this has been useful, I think, for higher level users who don't necessarily want to be exposed to a lot of this complexity, even though most of the people in this room would probably love to be exposed to that complexity. So if you do, come and talk to us. Thanks very much.
Awesome. Well, thank you. Maybe, is there any questions out here? Then I can pass out the mic.
I'm just curious about the UI. What do you guys use for the UI? Scala JS maybe or not yet? Or what's the plan?
You're talking to precisely the wrong people here. But
So we're just using JavaScript in the libraries. We want, frankly, at one point last year, we want to see whether we can use leveraging Scala JS, but we didn't get there. We did invite Howie to give talks and internally, and as well as we did a few hackathons and tried with Scala JS. So, but didn't get into production.
Can you talk about data visualization, how you're planning to do that? Where do you do the transforms? What, maybe you're the wrong people to ask about what UI you're going to use, but.
Well, actually, this project, the visualization project, is called the Chiasm. It's a D3-based open source framework, and you actually can directly go to the GitHub to find it. So on top of, it's a visualization uses D3, and there's a configuration. So when you can tweak the configurations, actually change the graph, and you change the graph and change the configurations. The stuff we talk about the leveraging the interactive, talking to and actually accessing the data. That's the pieces that we decided to run, because we had, unlike the other, everybody else in the room probably, they either run standalone Spark mode or on the Mesos or a Yarn client, so we have to run Yarn cluster mode. So the challenges is, start a Yarn container, take about, few seconds, and then Spark starts. So it's not a good way of doing the interactive visualization. So what we decided to do, essentially do a long-running Spark jobs. So keep the job start running, and then sending essentially additional messages without restarting the container. So that work is in progress, and we haven't really finished it. That's why we couldn't present it here. So that work combined with the Chiasm, open source Chiasm, so gives us a way of basically very quickly to dice and interactively see the data quickly, change different shape, different, view differently rather than statically display the results just calculated. So that also leveraging our workflow behind the scenes, so basically saying, I can run very simple Spark SQL jobs, or basically I can run whole workflow and then visualize this. It depends on what kind of type of work you want to do.
So essentially, there's sort of two layers to the visualization engine, if you like. The top layer, as you would imagine, is essentially a JavaScript or D3-based mechanism for doing rapid, interactive visualization of data. And that you can, if you do a search for Chiasm online, you'll see the open source code around that and can monitor the progress of it. And then there's a back-end piece, which is essentially sampling data out of the underlying data sources so that they can reach the browser and be fitted into memory.
We have a meetup for this on the San Francisco Big Analytics on September 17th at Alpine Data Labs. So if you want to find out more, you can join. You can come.
So if there's no more questions, maybe you guys can just join me in thanking Stephen and Chester for their talk.